Okay, so now that we've talked about limits, we understand how to evaluate limits, we're ready to start introducing the derivative. So if we remember back to the beginning of chapter 2, we were talking about average velocity and instantaneous velocity, and we found to find the average velocity, we were really just finding the slope of the secant line, which was f of b minus f of a over b minus a. We also use some other notations. We could have said x plus h minus f of x over h minus x. To find the instantaneous velocity, we were finding the slope of the tangent line, which was the limit of the secant as that difference became 0. So again, looking at a picture, the green lines are all my secant slopes, and I'm taking that difference between my points, that one to this one to this one, to figure out my instantaneous right at the point 180 to get my instantaneous velocity, the slope of the tangent line. So again, just showing us our picture, the slope of the tangent line gave me my instantaneous velocity over here, and it was as that distance got closer and closer and closer, so I was getting, I started with a point way over here, and I kept making the difference between my x values closer and closer and closer until it was right at that same point to get my instantaneous velocity, which was the slope of the tangent line. And again, here were those formulas. The average rate of change was our slope of our secant. The limit as x approached a was the slope of my tangent line. And now we want to find the slope at any point. And finding the slope of a curve at any point is what we call the derivative. So the definition for derivative is that f prime of x, that's our notation we're going to use for derivative, is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now this piece here should look pretty familiar. This is our formula for the difference quotient. Right, so we did a lot of work with that difference quotient because we're going to be using it a lot here so we can calculate derivatives. Okay, our most common notation for a derivative of a function is f prime of x, so that little apostrophe we use is called prime. It can also be written as df divided by dx, which means the derivative of the function f with respect to x. Alright, so let's do some practice finding our derivative. So the formula said to find f prime of x, I'm taking the limit as h approaches 0 of f of x plus h minus f of x divided by h. So I have to plug this in. So the first thing I'm going to do is figure out what is f of x plus h. So that's going to be 2 times x plus h plus 1, which is 2x plus 2h plus 1. So if I'm finding my derivative, switched colors there, sorry about that. So I have f prime of x. I'm taking the limit as h approaches 0 of 2x plus 2h plus 1 minus 2x plus 1, all divided by h. I'm still taking my limit. I haven't plugged in the 0 yet, so I have to keep writing the limit part. So 2x minus 2x is going to be gone. I'm going to have 2h plus 1 and minus 1 when I distribute the negative is gone, so I have 2h over h. So this is the limit as h approaches 0 of 2, and once I plug in that value, I just get 2. So that means the derivative for any point on this graph is f of x equals 2. So the slope of any line along that straight line is 2. Alright, let's try another one. So again, I'm first going to figure out what's f of x plus h. So that's x plus h squared, which is equal to x squared plus 2xh plus h squared. So to find my derivative, f prime of x, I take the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Cleaning up, I see that my x squared and my negative x squared add to 0, so I'm left with 2xh plus h squared. So I'm going to factor out the h from the numerator, and I'm left with 2x plus h divided by h. My h's simplify, so I'm taking the limit as h approaches 0 of 2x plus h. Notice I'm still writing limit, and now as I plug in the 0 value, I don't have to write limit anymore, so this would just be 2x plus 0, which equals 2x. So my derivative for any point on this curve, y equals x squared, the slope at any point will be equal to 2x. Okay, so same one, example 2, f of x equals x squared. So we know our derivative, f of x is equal to 2x. And now we want to find the equation of a tangent line at the specific point 3, 9. So the first thing I need to know is what is the exact value of the slope at that point. So to find my slope, I'm going to do f prime of 3. So 2 times 3 is equal to 6. So I know that's my slope. And then I want to find the equation of the line, y equals mx plus b. So I plug in my values. Y is 9, my slope is 6, my x value is 3. So I have 9 equals 18 plus b. So I know b is negative 9, that's the y-intercept. So the equation of the line tangent at the point 3, 9 is going to equal y equals 6x minus 9. Okay, so besides being able to algebraically find the slope of a line tangent to a curve, finding the derivative, we also want to be able to do it by looking at the graph. So if I'm given the graph of f of x, I can find where the slope has to be equal 0. So that would be any max and mins. So right here I have a slope of 0. Right about here I have a slope of 0. And right about here I have a slope of 0. So as I make that graph, anywhere the slope is 0, I know I'd be hitting the x-axis. And then I have to think about what's happening to the slope in between those values. So right here in this direction, this is a positive slope, so I know it's going to be above the curve. Over here, between these, this is a negative slope, so it's got to be down here. Again, here I have a positive slope, it's increasing, and then here I have a negative slope, so it's decreasing. So I know my graph is starting above. It's got to come down. It has to somehow bottom out if I'm going back up to 0 and cross back. So this red line, I'm going to highlight that because that's a little bit hard to see. I'll highlight it in green. This green would be the graph of the derivative for that purple function. Let's try another one of those. So again, the first thing you want to do if you're trying to get the graph of the derivative from the graph of the function is look for where it's 0. So I know I have a 0 right here and a 0 right here. Anywhere the graph has a max or a min, the tangent line is going to have a slope of 0. So right here and right here. So at negative 2 and just before positive 1. So over here, since it's multiple choice, I can look over here. So at negative 2, it has to hit 0. It does. It does. It doesn't hit 0 at negative 2 here, and it does here. Okay, we got 1 eliminated. That's good. The other one is just before 1. It has to be 0. So that one's pretty close. That's pretty close. All right, those are all pretty close. So then we have to see, okay, how do we know which of these is the correct one? So the next thing you look at is what's happening between the zeros. So from negative 2 to positive 1, this is a positive slope, which means over here, under my choices, the graph has to always be positive between those two values, which in this case it is. Here it's negative, so now I've eliminated a second one. Now if I look a little bit closer, it looks like right here I actually have another 0. So it's going to go negative, 0, and then positive again. And so this is right before number 3, which is just here. So I know this is the graph of my derivative. Now, if you remember back when we were talking about limits, we said that a graph could have a limit even if it wasn't defined at that point. But when we're dealing with continuity and derivatives, if f is differentiable at a value a, then f has to be continuous at a. It can't have a jump. Versus before, we could have a graph that might have looked something like this, and it had a 0 here, and it approached, and there was another point. That was not a continuous graph, but we could find the limit at a certain value a. However, we would not be able to find a derivative there because it is not continuous at a. So if f is not continuous at a, then it is not differentiable at a. Okay, so we have f of x equals the absolute value of x, and we want to find the derivative, f prime of x. Well, if I sketch the absolute value of x, it's a V-shaped graph that looks right here. Now, although this is continuous, I can draw it without lifting up my pen. It's not technically a continuous function because I have a cusp right here. It can't have any sharp points, which means right at that value, when a equals 0, this is not differentiable. But everywhere else it is. So I'm allowed to find the derivative as long as I know that I'm never allowed to do it when x is equal to 0. So note that the absolute value of x is actually equal to the square root of x squared. So I can rewrite this problem as f of x equals the square root of x squared, and then I need to find f of x plus h, which will be the square root of x plus h squared, which is x squared plus 2xh plus h squared. So now to find my limit, my derivative, I use the limit formula. So f prime of x equals the limit as h approaches 0 of the square root of x squared plus 2xh plus h squared minus the square root of x squared all over h. Okay, so this is one of those radicals, so I'm going to multiply by my conjugate. So my conjugate is the square root of x squared plus 2xh plus h squared plus the square root of x squared, and I'm doing that numerator and denominator. So this is equal to the limit as h approaches 0. When I double distribute, I end up with x squared plus 2xh plus h squared. The middle terms drop out, minus x squared, all over h times the square root of x squared plus 2xh plus h squared plus the square root of x squared. I'm not distributing. In my numerator, the x squareds simplify out. I'm going to factor out an h, so I'm left with 2x plus h over, whoops, bad notation. I forgot my limit sign. I got to squeeze that in there. Since I'm still taking the limit, I absolutely still have to have the limit as h approaches 0 in there. There we go. I'm sneaking that back in. Over my h times the square root of x squared plus 2xh plus h squared plus the square root of x squared. I know that's really hard to read. Sorry about that. Cancel out my h's. Now I'll be able to read it. So I have the limit as h approaches 0 of 2x plus h over the square root of x squared plus 2xh plus h squared plus the square root of x squared. And now I'm going to plug in the 0 for h, so now I do not have to write the limit anymore. So I'm going to have 2x plus 0 over the square root of x squared plus 0 plus 0 plus the square root of x squared, which is 2x over 2 square root x squared. My 2's simplify. So this gives me x over the absolute value of x. Remember, the square root of x squared equals the absolute value of x. So this is why x can't be 0, because that's where it's not continuous. The function is not continuous. But on the left side of my graph, over here, this always has a slope of -1. The right side always has a slope of +1. And if I plugged in any x value, let's say -4, -4 divided by the absolute value of -4 would equal -1. If I looked on the right side, +3, 3 divided by the absolute value of 3 would be a +1. So I can differentiate this, but I have to recognize that it doesn't work when x is 0, because this graph is not continuous at x equals 0.